Ladies and gentlemen, welcome to Physics Rocks. It's true, it's Tuesday night and it's nuclear fission and nuclear fusion, the last topic on the Year 11 syllabus for CCEA. So our objective tonight is to tell you all about how you make nuclear power, either through nuclear fission or through nuclear fusion. But before we get started at that, I want a quick recap on how we make electricity just in general. Now, there are lots and lots of different ways to do it, but by far the most common way to make electricity is 1. Get yourself, not a circle, but get yourself a vat full of water. Okay, so there's a little vat, there's a little rectangle inside it, and here comes some water. Bang. Right, we've got a vat full of water. Then we're going to heat that water pretty hard. Heat that up, and apply some heat to that. That's going to cause our water to start to bubble, and it's going to generate some steam. Alright, once we've got that steam, what we're then going to do is we're going to let that steam out through a very small vent that we make for it. Okay, so all the steam is going to get forced across this way and forced up through here. We're going to build a little pipe around this so we can actually direct the steam where we want it to go. Okay, we've got this very, very hot. This is not like the steam coming out of your kettle. This is seriously high-powered, pressure washer type stuff, just really, really hot. Then we're going to send that into some form of twirly thing. Okay, we call it a turbine because twirly thing sounds a little bit on the non-scientific front. So we make a turbine, and when the steam hits the turbine spins. Okay, the turbine is connected to a little cylinder, and inside that cylinder there's a spinning magnet and a coil of wire. And that spinning magnet and coil of wire inside is collectively known as a generator. This is how we're generating electricity. Okay, so objective 1, heat water. Objective part 2, water evaporates, turns into steam. High pressure steam spins a turbine. Turbine spins a generator. Hey presto, we've got ourselves some electricity. So what's our input here? Okay, well, we built all this, and we might need to top it up with water occasionally, but really the energy input is heat. If we can figure out a way to heat up our water, then we've got an electricity source. Okay, if we can figure out a way of heating up our water that requires less input energy than we would get out in terms of generator. So, for example, we could use coal. Coal is an excellent way of doing this. It's a whole pile of chemical energy that was dropped to Earth ages ago. Old plants and animals absorbed that sunlight. Okay, put it into themselves. They got fossilized. That chemical energy got trapped. And all we do is set it on fire to release that energy. Okay, remember the conservation of energy still applies. This energy isn't, we're not creating energy in this process. We're just releasing stored energy here. And that's how we would do it with fossil fuels. Okay, we do it with oil, we do it with gas, we can do it with peat if we really fancied it. We can just make heat and away we go here. All right. Renewables try to avoid this heat part here and maybe connect this turbine thing up on a big mast and let the wind turn it. But it's broadly speaking the same process. And nuclear fission and nuclear fusion aim to run this exact same process, except what we're going to do in nuclear fission and nuclear fusion is that we're going to find rather novel ways of generating heat. Okay, so nuclear fission, what is it? Well, first of all, we need to go to our little nucleus because it is nuclear fission. And inside the nucleus of an atom, we have a variety of nucleons. That is, the things that live inside the nucleus of an atom are called nucleons. Some of those are positive, they are protons. Some of them are neutral, and they are neutrons. None of them are negative because negative electrons do not live inside the nucleus. So we don't really care about these because we're nuclear physicists, and we'll let the chemists deal with their little electrons. Okay, nobody cares. Their mass is negligible. All right, now, once we get to very big nuclei, very big, and of course we say very big comparatively speaking, compared to like hydrogen. Once we get up to your uraniums and your plutoniums in the periodic table, there's a lot of things going on in this nucleus. You've got, well over 100, 150, 200 nucleons going on in here. Right? And there's no negative charges to balance anything out. There's a lot of positive charges. This thing's getting bigger and bigger and bigger, because it has to accommodate these, so the diameter of our nucleus is getting large. And as a result of that, it's becoming harder and harder to keep this nucleus together. And nucleus is hard to keep together. That means that it's likely to break up in some shape, form, or fashion. Now, we've already discussed in some of our other live streams about how this can happen, in that if we have too many protons, we can kick out 2 protons, grab them, and a couple of neutrons to go with it, grab them too, kick them out as an alpha particle. And that's alpha radiation. Or perhaps we have too many neutrons, and one of our neutrons can undergo a transformation where it turns into a proton and then kicks out an electron, because remember, electrons aren't allowed to stay, and that comes flying out of the nucleus and is a beta particle in beta decay. But nuclei and large nuclei are a little bit like unstable relationships, because there's lots of unstable relationships going on in here. And yeah, you can tweak around the edges and you can change bits of you here and there, and you can get rid of certain habits and get rid of certain things. But there comes a point when realistically the only sensible thing to do is to split up. Right? That this nucleus is too big. There's no amount of alpha radiation or beta radiation that can sort it out in time to stop it flying apart. And we get a breakup. The nucleus splits in half, and we can't just call this nuclear splitting, because again, that makes us sound as if we're normal. We call it nuclear fission. Okay, where fission means splitting. And we're going to split our nucleus. And this happens to quite a lot of atoms a lot of the time. They just break up. And bits of them go one way and bits of them go the other way. Right, so in this split up here, you get a crack down the middle, and then that goes on to, out comes a couple of random shards that will go on to form 2 new nuclei, and then you might get some little bits and bobs left over that didn't make it into either, something like that. Okay, these sections here, these are called, all of this, these are called fragments. Pick up the fragments of your broken relationship. Right, so we've got a main nucleus here, breaks up, forms a couple of small ones, and some fragments. Right, well, that's fabulous. Why would anybody care about this? It's probably happening in the room around you right now. And the little nucleus here was sitting still, it cracks open, and these things here fly off, and they're going like a bat out of hell. Like they're really, really hauling. They're moving quite quickly. And that's one of the reasons that we're interested in it. Because this movement energy here can be transferred to other things. Because remember, movement energy inside molecules and inside atoms is heat. So, and remember, we're looking to generate heat. So we had something that wasn't particularly warm to start with that has now got more kinetic energy. It's got heat. Well, the first question is, how did it get that? Where did it get that from? Because remember, energy can't be created, it can't be destroyed, it can simply be changed from one form into another. So suddenly, where did this movement energy come from? And where it came from was that if we had a certain mass, m, let's imagine that the mass here is represented by the letter m, here, the mass before of my original nucleus, then it would make sense that if we call this mass A and this mass B, that we'll call these little ones here C, D, and E, then it would stand the sense that M would equal A plus B plus C plus D plus E. That is, if you could pick up all of the random bits and bobs that you've just broken up from a nucleus and shove them back together again, you'd have the same thing, okay, mass-wise. And that is not true. It actually turns out that the total mass of this whole system is actually a little bit greater than A plus B plus C plus D plus E. And this is weird. This is really weird. Some mass has gone missing. All right, some mass has hidden under the celestial duvet and just gone, no, I can't handle it. I'm hiding. And this is what this equation is all about. And everybody watching, unless you've lived under a rock or you've accidentally clicked on this video, has seen this equation. To be honest, some of you have accidentally clicked on this video and have seen this equation. E equals mc squared. Einstein's famous equation. And what his equation says is that energy and mass are interchangeable because they are fundamentally the same thing. And that the amount of energy I have is equal to the amount of mass I have in kilograms multiplied by the speed of light squared. The speed of light squared is a very, very large number. Okay, it's something like 9 times 10 to the power of 16. Okay, that is a 9 with 16 zeros after it. That is a big number. Now, the masses that we're dealing with here are very small numbers, and therefore the energies we're dealing with for a single atom are very, very, very small. But this big number is going to help us later. And what's happened is that some of the mass that was in this original nucleus has been converted into energy. And that energy we're seeing as kinetic energy in these particles. Okay, so we've converted mass into energy. And that's what nuclear fission is all about. It's about breaking down a large nucleus and turning some of the mass that's in that large nucleus into energy that we can then extract. The problem is that nuclear fission is a random event. Okay, it's a bit like radiation. Some nuclei are too big and they'll randomly fission and give out some energy. And the energy they give out is large by comparison to them, but crap by comparison to what we would like to use it for. We would need trillions, gazillions, numbers that have no name of these events to happen every minute or so for us to generate any form of electricity of it. And the random nature of it doesn't let that happen, which is a good thing, because if the random nature of it did let that happen, then random uranium deposits all around the world would just randomly explode, which would be bad news for anybody living anywhere near them. If you're just walking across your living room and then a little bit of radium that's in the ground below you just decides to turn itself into a nuclear bomb, that would probably ruin your day. Okay, so we need a system of making this happen. That's what the entire physics of nuclear power generation is about. And it's actually quite simple. There are a couple of atoms that are stable-ish. Okay, by atoms I mean nuclei. Okay, there are a couple of nuclei that are sort of stable. They're like that supply teacher you get, when your teacher's off, and this person comes in and they sit down at the chair and they look all right, and then you try your general best to wind them up a bit, and they're all right, they can handle it, they can deal with it, but then somebody says something and you can see the little twitch happen in their face, that they're just about to lose it, that they're just sitting on the edge a little bit, and then there's that one person, we'll say person because this is a family friendly show, that just decides to push them over the edge, and all hell breaks loose thereafter. That's what we want. That's what we want. We want a nucleus like that, that's stable but right on the edge of cracking up. And there are a couple of nuclei that are really good for that. There's uranium and plutonium. Okay, thorium as well, but we're not really going to touch on that too much. And this is stable, but with a little tap in the right direction, it's going to break up. So we're going to give it a tap. We're going to take a neutron, just one, and we're going to fire it into here. Okay, one neutron is going to get fired into the nucleus of this. Okay, how we go about doing that is a big technical challenge. Okay, but we'll get it done. We'll get it sorted. Okay, we're going to push that into our nucleus like that. Okay, should be a bit bigger. And, well, it appears that there's no more room at the end. The introduction of that one neutron sets off a fission event. This uranium will crack and split, and out of it will come a couple of fragments that are moving, so therefore they have kinetic energy. Some of the mass has gone missing, just as we said, and there will be some leftover bits. And this is why uranium's really good for it, because what it'll do is it'll have some leftover neutrons that don't get absorbed into this or this. Statistically speaking, we'll always end up with 2, maybe 3 neutrons left over. And this is the genius of it. Because if you can get enough of these uraniums in one spot, if you fire a neutron in and break this one up, then it produces a couple of these big fragments that we can get energy out of. I'll color them in differently so we understand that these are big fragments. And then the neutrons that are produced can go on and can travel and can run into other uranium atoms or uranium nuclei, causing the exact same process. Except where we put in 1 neutron, we now have generated 2. And these 2 will generate 2 each, making 4. And we rapidly end up with a situation like this, that we start with 1. In fact, let's get a slightly better looking little picture. And we start off with 1 nucleus, and we fire into it a single neutron. Make that neutron quite small, so I want this diagram to come big. In that goes. Then this will fission. It will create a couple of other nuclei. So I'll bring in some little spheres for that. A couple of other nuclei. They're going to be our energy carriers. But more importantly, we'll generate a few more neutrons. These neutrons can then go on, and if we've arranged everything correctly, they can travel into further nuclei and cause exactly the same thing to happen again, that we get some fragments that are carrying kinetic energy for us, and we can extract that kinetic energy, and we'll talk about how we do that in a minute. But each of these then will also produce 3 more neutrons, which means my next layer down is going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 of these. Assuming I can capture all of my neutrons, which I almost certainly can't, but in principle, we could then do this. And you can imagine what the next level of this diagram looks like. They're absolutely hellish to draw. But we have a try at it anyway. We're not going to bother drawing the big red ones, because then it's just completely colored. But that will produce 3 neutrons, and 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 that will produce 3 neutrons. And you're all thinking the word neutron sounds like a bit of a weird word now. And we now have a huge section of these, which can go on to create more and 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 more fission events all the way across the board. And this is what we call a nuclear chain reaction. This gets out of hand pretty majorly, because if the amount of energy created here is E, then the amount of energy created here is 3E. Yeah, because there's 3 times as many being split. But then this level is 9E, and the next level will be 27E. and the next level even more, and the next level even more, and we get a runaway reaction where a huge amount of energy is released, and this takes very little time. Okay, this is called a chain reaction, and is the essence of how a nuclear bomb works. That you simply let this process run out of control. The energy produced is so large that you get so much heat, you get a bomb that makes all of chemistry a complete joke. That, to give you an idea here about what we're talking about, when you're talking about nuclear weapons, you tend to measure them in things like megatons. Right? You know, you get a megaton nuclear weapon. But it doesn't weigh a megaton. A megaton's a million tons. It definitely doesn't weigh that. You know, it's a single bomb. What a megaton means is if you had a megaton of dynamite, it would produce the same explosion that this bomb is going to produce. Okay? To make an average nuclear weapon out of regular chemistry, you would need 1,000,000 tons of standard explosive to rival this. Okay? That's why this is worth looking at. Now, we don't want to blow things up, broadly speaking. What we want to do is we want to use this for energy production. We want to control this process. And controlling this process is the essence of how nuclear power plants work. And the game is this: to let the reaction run until we get to a stage, say here, where we've got enough heat to heat water. Like really, really well. It has to be very, very hot. We're going to heat water like nobody's business. We're going to be the masters of heating water. But we don't want it to get out of control. We don't want a bomb. We just want something really, really, really hot. So all we need to do at that stage is to go, right, we're happy with this set here. So what we need to do is in the next level, we need to allow the same number to continue. But then all the rest of this stuff that's produced, we're going to need to soak these neutrons up. If we can soak them up and get rid of them, then this layer can't happen. And all we'll get is 9 more, and we'll end up in a loop that runs back to here. I'll do that in a different color just so that we're all following. That we end up looping right back round to this step up here. And we get stuck in that loop. We go, there's 9, loop back round 9, loop back round 9. 9's obviously not the number. Okay, the number is much, much higher, but this is an idea. Does that make sense? I hope that makes sense. Okay, and this is a nice, sustainable nuclear process that we're generating heat, but we don't have a runaway bomb. We need enough material to keep as if a bomb was going to happen, just to keep this whole process running and running and running. And back to our original then, once we've got that running, we've got heat, and we can boil our water. Okay, so what does it look like? Well, remember, we're using something like uranium or plutonium or something like that, and they're metals. So what they are really is just cylinders, rods of metal. We call them fuel rods. And as the reaction gets underway, the rod gets warmer and gets warmer and gets warmer, and it warms up, gets hot. And as it gets hotter and hotter and hotter and hotter and hotter, you either submerge it in the water, or to be honest with you, you actually put it into a gas, something like carbon dioxide that carries the heat up to the water, or through to the water through a heat exchanger. We'll learn about that at A level. But at GCSE, we heat the metal. The heat from the metal then travels up into the water, boils it, and away you go. If you've got too many neutrons, you put a material in to actually absorb some of those neutrons. Something like boron's a really good example of this. Okay, so you stick that in, and then the wee neutrons are created. You slide that into the middle of it. You have this hollowed out. You slide that into it, and then any of those neutrons get absorbed. And if you're absorbing too many, you pull the boron out a bit. And if you're absorbing too few, you push them back in. Now, how do you know if you're absorbing too many or you're absorbing too few? Well, that's actually really, really simple, because all you do is look at the temperature gauge. Okay, so you have a little temperature gauge that's got a needle. Okay, over here on this side is too cold, In the middle here is perfect operational temperature, and on the far end we have everybody dies. So the needle ideally wants to be here, but if you're absorbing too few neutrons, it'll start to creep this way. So you put the boron rod in a bit, and then it comes back this way, and then across that way because you move it out a bit. And the game is to just keep that needle hovering in the green zone. And that's pretty much computer controlled. Then you'll have a person watching the computer just in case it messes up, just to keep everybody safe. Alright, and that's nuclear fission. That's all there is to it. Okay, game of nuclear fission. Take an unstable nucleus, put a neutron into it, or get a semi-stable nucleus, put a neutron into it, cause a fission event. That will then create more neutrons, which go on to create more fissions. That's a chain reaction, and then start to siphon off some of the neutrons when you're happy with that. Okay, so that sounds great. That sounds great. So why wouldn't we always do this? Like, why isn't that the main thing? Okay, because pros of all this, that nuclear energy creates no greenhouse gases. Now, that's a little bit of a lie. The actual process doesn't. You're just heating water using a metal. But mining and refining and transporting your materials does create some greenhouse gas. Nothing you can do about that. Okay, but in theory, I suppose if you were using electrical stills and you were using electrical equipment for the extraction of the uranium and you were using electrical equipment for transporting it, you could argue that the whole thing could be, at least in theory, greenhouse gas neutral. And it's certainly not as bad as coal, oil, or gas. Okay, that this is a high skilled job. Okay, so you create lots of jobs of high skill, which is great for your economy. It's great for your workforce. It's for that there. So you get really good high skill jobs, which is what we want, and that's lovely. Okay, so we've got jobs, we've got high skill, we've got the fact that it lasts longer than coal, oil and gas, and it certainly preserves them for the other things that they're useful for. Right? It's not renewable, but it's in that. Okay, we've got some cons though. The cons are pretty major. There's the risk of a nuclear incident. Now, no nuclear power plant has ever blown up, but there have been 3 high-level nuclear incidents. And when you have a nuclear incident, you put radioactive material around the place. That makes it, the area around the nuclear power plant basically uninhabitable for a set period of time. So that's a big, big deal. And because of that, we have what's called the NIMBY argument, which is not in my backyard. Some people are super interested in nuclear power and like the idea of it, but if you were told that tomorrow they're going to start building one 1 mile away from your house, you might change your mind on that. Okay? So there are problems with that. Other major problem is there's a huge capital investment. That to build one of these things is a huge amount of money. You need to recoup that money over the time that you have your power plant running for. Right? So there's some good things and some bad things about nuclear power. The other nuclear power that we want to talk about is nuclear fusion. And it's getting a little bit more press these days. Nuclear fusion it's almost the exact opposite of nuclear fission. Where nuclear fission takes a big unstable nucleus and breaks it apart to generate energy, nuclear fusion takes 2 very small nuclei and rams them together to generate a larger one, like this. And they have to be small nuclei. So we're looking at kind of hydrogen level stuff. And in fact, we're almost looking at hydrogen that has 2 hydrogen, normal hydrogen, and maybe hydrogen 3 and hydrogen 2, which are isotopes of hydrogen. That this is 1 proton, 1 neutron. This is 1 proton, 2 neutrons. These are called deuterium and tritium, which are the second and third smallest nuclei you can get. The smallest being just hydrogen, which is a pure proton. I'm going to cram these together and make a larger nucleus. We're going to make some helium here. Okay, because we've got two protons, we've got a proton there, cram it together, we make some helium. And again, if we call this, if we say that this has a mass A and this has a mass B, then this one has a mass of C. And the cool thing about this is that the mass of A plus the mass of B is in fact slightly greater than the mass of C. The mass you had before is slightly greater than the mass you have after, because some of the energy or some of the mass is converted into energy. And again, it's converted into kinetic energy in this outgoing helium. And that speed we can then turn into heat. Exactly the same process. Right, so why is this good? Well, this is good because we're using hydrogen, which is essentially the most abundant element in the entire universe. Now, to be fair, we're using quite exotic hydrogen, not your run-of-the-mill stuff that you just gather up, but this is readily available. Okay, you can get this from seawater, and you can actually generate tritium from lithium. You can do all sorts of fun things. Okay, this is super readily available fuel. There's no radioactive material produced here. This reaction does produce a little bit, actually, a tiny little bit of short-lived radioactive material, but certainly nothing by comparison to what you'd expect from a nuclear fission reaction. Right. There's so much fuel available in abundance for this that while it's not renewable, if you run out of hydrogen in the universe has ended. Okay, life doesn't work the way it used to work, so you've got, for all intents and purposes, unlimited fuel. Okay, this process could solve all of mankind's energy problems. There's a slight problem. It's one of the oldest jokes in physics that fusion is about 50 years away. And it has been about 50 years away for around about the last 50 years. That a breakthrough in nuclear fusion just hasn't come. And it seems to be getting closer, and it seems to be getting closer, and it seems to be getting closer. Everybody gets very excited about it, but it just never quite makes it there. And the reason for that is that you're taking a positive nucleus and you're trying to push it together with another positive nucleus. And the amount of force and pressure and input energy required to do that is enormous. And the amount of energy you get out at the end, for now, is less than the amount that you put in most cases. Now, the sun does it. Using huge amounts of gravity, it can make this process yield energy. Okay, that more energy comes out of the process than went into it in the first place. Now remember, we're not creating energy, we're just changing mass into energy. We're not creating it. We're simply converting mass into energy. And the net energy output for the sun is greater than the energy input. Eventually the sun will run out of fuel, and that'll be the end of it. Okay, there's no magic going on here. Eventually it will run out of fuel. On Earth, we can make this work in a nuclear bomb, in a hydrogen bomb, for a period of time, but to make it in a way that's controllable to heat water for long-term electricity use remains something that we can't do. There are projects like the ITER project that are trying to get this to work. And it's getting better and getting better and getting better. But this is taking huge amounts of time. But why are we interested in this? Why are we interested in this? Well, there's a couple of reasons. Fusion releases 4 times the energy per kilogram than fission. Okay, so nuclear fission not only produces radioactive waste, not only makes everybody really nervous and is non-renewable, but this thing is 4 times more energy productive per kilogram of fuel. And nuclear fission is already extremely fuel efficient. Okay. The other thing is it is 4 million times more energy per kilogram than fossil fuels. Now just let that sit with you for a minute. That per kilogram of fuel, you get 4 million times more energy than you would from a fossil fuel. This is worth it. We fix this. We get this working. Suddenly we have electric cars across the board. No issue. We have fusion rockets that take people to space. Okay? We have the ability to put colonies on other planets because mining hydrogen is something that can be done. This problem solves more problems for mankind than almost anything else. Okay, this is the invention of fire as far as human advancement goes. We can solve this and make it happen. I firmly believe that humanity will take a massive leap forward. Now, it doesn't mean to say that your energy will be free, because whatever we build that does this reaction will be astoundingly expensive. Okay, so building the reactor that makes this happen will be ridiculously expensive. So you're going to have to pay for your electricity still. You have to pay for your energy somehow. But this fuel source is disgustingly cheap. So once you've got it up and running, the running cost should be pretty small. So all you're really doing is getting your capital investment back. So if you've got a reactor and it's got a good lifespan, you can realistically look at energy being really, really, really cheap. Okay, that's why this is important. So nuclear fission, and recap, nuclear fission, you take a large nucleus, let's run ourselves back, take a large nucleus, you split it, some of the mass goes missing, that mass gets turned into heat energy, you use that to heat some water, turn a turbine, run a generator, make electricity. You want to pick a material that not only produces high-speed flying fragments, but also produces extra neutrons, so that those neutrons can create more fissions. Good things, no less greenhouse gases, high-skilled jobs, last longer than coal, oil, or gas. Bad things, there's always the risk of radioactive accident, produces radioactive material, nobody wants it anywhere near it, you got a big capital investment. Nuclear fusion, we take two small nuclei, ideally deuterium and tritium, cram them together to make a helium. Some of the mass goes missing and is turned into energy. That energy we can use to heat water and run turbines and run generators. We can get 4 times the amount of energy per kilogram than in fission, 4 million times more energy per kilogram than fossil fuels. But we're still about 50 years away because pushing these two things together is ridiculously difficult. It can be done, but to get it done in such a way that the energy you put in is less than the energy you put out is very, very, very difficult. Okay, and if anybody can solve that problem, there is a Nobel Prize and untold amounts of wealth waiting for you. So I'll let you mull that one over, have a little think about it. If you can come up with an idea, don't tell the government, tell me, and I absolutely will steal your idea and make my millions, because no ad revenue in this channel, because I'm that type of guy. All that remains for me to say is thank you so much for those of you who have tuned in this evening to watch. I massively appreciate a like for no reason other than it makes me smile. And don't ever forget that physics rocks. It's true.